Hello, everyone, and welcome to this deep dive into continuous time finance. Today, we'll be exploring the fascinating relationship between two pillars of modern financial theory: the fundamental theorem of asset pricing and Girsanov's theorem. We often celebrate the Black-Scholes formula as a hallmark of option pricing, but there's a deeper question lurking beneath it. How can a single formula or any pricing approach exist without giving rise to instant riskless profit? In other words, what ensures that markets, volatile, complex, sometimes irrational, can still be modeled in a way that's consistent with the idea of no arbitrage? The answer rests on the framework of measure theory, shifting from the messy, real-world probability measure to a risk-neutral probability measure. And that shift is powered by the math behind Girsanov's theorem. So think of this talk as a guided tour of market modeling, culminating in the grand statement we'll refer to as the fundamental theorem of asset pricing. By the end, I hope you'll see that the foundation of derivatives pricing is every bit as elegant as it is practical. We introduce the foundational setting for our entire framework, a complete filtered probability space, where capital P is our real-world measure. Think of omega as the grand library of every possible market scenario, and script F as the labeling system that tells us which chapters are relevant at each moment in time. The notation script F sub t means the information we have right up to time t. Within this space, we define a standard Brownian motion, spelled W sub t, capturing the unpredictable fluctuations of the market. Finally, let capital S sub t be the price of some risky asset, like a stock or a commodity, that will soon be governed by a stochastic differential equation. In essence, this slide lays the probabilistic bedrock on which we'll build our entire no arbitrage argument: omega for the state of the universe, script F sub t for the evolving knowledge structure, and W sub t as our random driver. Ito's lemma, perhaps the brightest gem of stochastic calculus. Imagine we have a process capital X sub t that evolves under a small incremental piece, alpha sub t times dt, plus a noisy part beta sub t times dw sub t. Then consider a function f of t and x sub t, where f is smooth in both time t and the state x sub t. Ito's lemma tells us exactly how changes decompose into a drift piece and a random piece. In plain language, it's like performing a derivative expansion in classical calculus. But here we also account for the fact that any squared infinitesimal from the Brownian motion accumulates over time, leading to that extra half times beta sub t squared factor. This lemma is the key reason we can handle complicated transformations, like taking the logarithm of an asset price or discounting that price, and still track how the system evolves under randomness. The short version, Ito's lemma, is our toolbox for peeling away drift and volatility layers, letting us rewrite processes in a form that will become very convenient for risk-neutral pricing. Let's now describe how a risky asset moves in the real world, the world under the probability measure spelled capital P. The price process evolves according to a stochastic differential equation. ds sub t equals mu times s sub t dt plus sigma times s sub t dw sub t. Here, mu is the real-world drift, the average expected return of the asset. Sigma is the volatility, capturing the randomness or turbulence we see day to day. W sub t is Brownian motion under the real-world measure capital P. When we apply Ito's lemma to the natural log of the price, written log s sub t, we find something beautiful. The drift becomes mu minus 1/2 sigma squared. That half sigma squared term appears purely from the curvature of Brownian motion itself. This is the true structure of asset evolution in the physical universe. But as we'll soon see, for the purpose of pricing derivatives, we don't want the real-world drift mu. We want to enter a new world where the only growth is at the risk-free rate. That's the goal of Girsanov's theorem. Every complete financial model needs a safe asset. In our case, that's the money market account, denoted capital B sub t. It earns interest at a constant rate, little r. So the differential equation is dB sub t equals r times b sub t dt. Solving this gives b sub t equals exponential of r times t. To make comparisons easier between risky and risk-free assets, we define a new process, the discounted asset price. That's ss tilde sub t equal to s sub t divided by b sub t. This tells us how the risky asset performs relative to the safe one. Now, when we apply Ito's lemma again, or use the product rule, we see that the discounted asset's evolution has a drift of mu minus r and volatility sigma. Said differently, under the real-world measure capital P, this discounted process still has a non-zero drift, and that's the problem. To eliminate arbitrage, we need discounted prices to behave like fair games, like Martingales. But right now, they're biased by mu minus r, so we must change the probability measure to remove that bias. This is where Girsanov steps in. Girsanov's theorem is the mathematical machinery that lets us perform a sleight of hand. We shift the drift of our stochastic process by changing the measure. To begin, we define the market price of risk. Theta equals mu minus r over sigma. Spelled, theta equals mu minus r, all divided by sigma. This quantity theta measures how much extra return you're getting per unit of volatility. Now we build a new probability measure called capital Q, using something called the Radon-Nikodym derivative. That's just a fancy way of describing how we twist one probability space into another. The formula is an exponential of minus the integral of theta times d w sub s minus 1/2 the integral of theta squared ds. This transformation effectively redefines Brownian motion. The new one, called w tilde sub t, is equal to the original Brownian motion plus the integral of theta over time. Substituting that into our discounted asset equation removes the drift entirely. Now, the discounted price process follows a pure Brownian motion with no directional bias under capital Q. That makes it a martingale. In other words, no arbitrage, no free lunch, and we're finally in the right universe for pricing. Now we arrive at one of the core insights in all of modern finance, the pricing formula under a risk-neutral world. Suppose you hold a derivative that pays capital X equals h of capital ESS sub capital T at time capital T. This could be a call option, a put, or something exotic. The question is, what is its fair value today at time lowercase t? The answer is clean and elegant. You take the expected value under the risk-neutral measure, spelled capital Q, of the future payout, discounted by e to the negative r times capital T minus t, and conditioned on the information available now, script f sub t. This is written v sub t equals expectation under capital Q of e to the minus r times capital T minus t times capital X, given script f sub t. This works because, in the world of capital Q, the risky asset has no risk premium. The drift mu is replaced by little r, the risk-free rate. And because we've made the discounted price a martingale, we're allowed to value it by a simple expectation. This is the endgame of Girsanov's theorem. It gives us a synthetic universe where the math is symmetric, time-consistent, and arbitrage-free. From this one formula, we derive everything. Let's now state the crown jewel of the whole theory, the fundamental theorem of asset pricing. In its continuous time version, it says this: a market is arbitrage-free. No free money. If and only if there exists an equivalent measure, capital Q, that is absolutely continuous with respect to the real-world measure, capital P, such that the discounted asset price is tilde sub t is a martingale under capital Q. Spelled out, no arbitrage if and only if there exists a capital Q, measure equivalent to capital P, under which the discounted price evolves without drift. Girsanov's theorem is what actually builds this measure, constructing capital Q from capital P by correcting for the drift. That drift correction, remember, was theta equals mu minus r over sigma. This theorem isn't just abstract. It's the philosophical bedrock of all modern pricing models. It tells us that if we assume no arbitrage, then a risk-neutral measure must exist. And if we find such a measure, we know our model is internally consistent. It's a powerful duality, mathematics at its most elegant and meaningful. Let's bring all the machinery together in one fully worked out example. Pricing a European call option. The payoff is capital X equals maximum of capital ESS sub capital T minus capital K, comma 0. That's the usual call option payoff at time capital T. Under the risk-neutral measure, the real-world drift mu has vanished, replaced by the risk-free rate, R. Integrating this gives us the terminal price, capital S sub capital T. This means the log of capital S sub capital T is normally distributed. That's log normal dynamics under capital Q. Now we define two expressions, D1 and D2. D2 equals D1 minus sigma square root capital T minus T. Then the final pricing formula, brace yourself. It's breathtakingly clean. Call price at time t, capital C sub t. Here phi is the standard normal cumulative distribution function, and that's it. A closed-form solution born from measure change, stochastic calculus, and no arbitrage. This is the beauty of the risk-neutral world made real. A world where pricing is probability and value is expectation. So there you have it. We started with a stochastic process for a risky asset, introduced a risk-free benchmark, and then, like a magician pulling probability out of a hat, we invoked Girsanov's theorem to shift the drift. That gave us a new universe, where discounted asset prices become martingales, and pricing becomes clean, expectation-based math. This whole dance is encapsulated in one glorious sentence. If there exists a risk-neutral measure under which discounted prices are martingales, then there is no arbitrage. That's the fundamental theorem of asset pricing, arguably the most beautiful expression in finance. More fundamental than black Scholes, more mysterious than mean reversion, and more elegant than your 401k on a good day. And yes, this is still me. Or rather, the AI version of me. The real Joel is probably off somewhere trying to divide by 0 just to see what happens. Here on this channel, we'll cover rigorous fundamentals like this, but also cinematic explorations of weird models and the occasional tangent. Because why not? I'm not here to give you financial advice. I'm here to make you fall in love with the math behind markets, and maybe a bit of overthinking. Oh, and before I go, why did the quant cross the road? To minimize variance on the other side. Thanks for watching. Subscribe if you're curious enough to wonder what elliptical integrals have to do with blackjack and mining Bitcoin. See you next time.